Yeah. Okay, so there's no going to be an echo or something. So it's all the audio coming on from my computer. Are there people able to hear me before? Okay. Let me hide this thing again. Okay. Yeah, so I'm going to use slides for my talk, and at some points I probably will use the board, but not a lot. So I guess people in the Zoom won't be left out a lot. I mean, maybe you should check a video if you see that I'm writing on there. Yeah. So mostly I'm going to use the board for the thing I do during my like previous couple of talks that happened in spring. So I usually start my public talks with saying glory to Ukraine and stop the war. Yeah, and now I'm going to start my talk. So I'm gonna speak about Harish-Chandra bimodules in complex rank. And when I say that something happens in complex rank, I mean that I consider it in the context of the Deligne tensor categories. So let me start with a quick overview of what is going to happen. So I'll cover some results from two of my papers. You can find them on archives, the most recent ones about Harish-Chandra bimodules. And I'll start with giving the preliminaries on the Deligne categories. I'll give all the definitions. I'll talk about the properties of these categories. And then I'll briefly discuss the ultra-product construction for the Deligne categories, which will use, it will be a very useful tool for proving stuff. And in the second half, we'll discuss Harish-Chandra bimodules, and I will give all the definitions, also for classical Harish-Chandra bimodules, as well as complex rank ones. And then I'll state the result about the classification of central characters of Harish-Chandra bimodules in Deligne categories. And lastly, if I have time, we'll talk about the so-called Harish-Chandra bimodules of finite K-type. So let's begin. So the categories, Webglt, Deligne categories, intuitively speaking, they're defined as interpolations of the categories of representations of the group GLM to complex value of the parameter m. And now more rigorously, we define it as follows. So Webglt is defined as the Karoubi envelope of the symmetric rigid monoidal category that is generated by a single object V that has dimension T. And we also require that endomorphisms of the K-tensor power V are precisely given by the group algebra of the symmetric group Sk. And Sk acts on the K-tensor power by permuting the tensor factors. Now, we also want that there are no homes between the K-tensor power V and the L tensor power V unless K is equal to L. So let me break down this definition a little bit. So when I say that we take the Karoubi envelope, I mean that we formally adjoin images of all idempotents, and we also adjoin finite direct sums of objects. And V has categorical dimension T means that if we compose coevaluation with evaluation, then we'll get the map from the unit object in our monoidal category to itself. And we require that this is a multiplication by the complex number T. And so we have this monoidal category that is generated by single object V. So it's rigid monoidal category. So every indecomposable object will be direct summoned in the object that I denote RS. That is just R copies of V, tensor product with S copies of V dual. So yeah, I want to remark on the fact that I only considering the category Webglt in my talk, but everything can be all definitions in result can be generalized to the categories rep OT and rep SP2T. So this is also dealing categories that are interpolate the categories of representations of our orthogonal and symplectic group. And we generalize this jointly with Serena Hu. Okay, so now let us discuss this category Webglt a bit more. We want to understand it better. So let us consider homes between this generating objects RS and R prime S prime. So by duality, it's this vector space is the same as the homes between R plus S primes tensor copies of V to R prime to S tensor copies of V. So we know that this is 0 unless the two sums are equal. And now we also would like to understand the algebra structure on endomorphisms of this generating object RS. And so what we will get is the so-called Wald-Brouwer algebra, BRST. So this algebra has a nice diagrammatic description, and you can just write down the basis for it. But I don't think I'll have time for this. But what we should know about this algebra is that, well, there's clearly an injective map from the group algebra of the product of two symmetric groups, SR and SS, into BRST. But this is because, well, there is an endomorphism of R copies of V tensor with R copies of S V dual, where we just permute the R copies of V and permute the S copies of V dual. So clearly we have this embedding, but it turns out that this maps actually splits. So we can we have a surjective map of algebras from BRST to the group algebra. And roughly speaking, what we should consider is the ideal that is generated by maps that, so we have, let me use the word now, but so we have maps from V, if you have more than, well, at least one copy of V and one copy of V dual and some other copies. So we can have a map that take evaluation of V and V dual, then we take composite with co-evaluation. So if we have, if we generate an ideal by all such maps that involve evaluation and co-evaluation, then the kernel of this ideal will be precisely the group algebra of the product of two symmetric groups. Still? So, okay. Okay. So if we now want to classify incomposable objects in Webglt, then it's the same as classifying primitive idempotency in BRST. And this was done by Combs and Wilson. And the result is the following. So recall that primitive idempotents in the group algebra of symmetric group are classified by partitions. So if you have a group Sk, so we can assign to any partition nu of k the idempotents which I denote z. Now, for any bipartition, that is just the set of two partitions, ordered set of two partitions, such that lambda is a partition of R and mu is a partition of S, we can assign a unique primitive idempotent, E lambda mu, in the Wald-Brouwer algebra. And so it is defined by the property that pi of E lambda mu, like this projection onto the symmetric, onto the group algebra, is the tensor product of Z lambda with Z mu. And note that because we had an embedding of the symmetric, of this group algebra of the product of two symmetric groups, this Z lambda tensor Z mu can be thought of as an element in BRST. And it will still be an idempotent, but it will no longer be a primitive idempotent. So we can decompose it into the sum of primitive idempotents. Then E lambda mu is the only thing that is mapped to something non-zero via pi. So, and this is the full classification of primitive idempotents in BRST. And as a corollary of this, we get that indecomposable objects in Webglt are labeled by bipartitions lambda mu, and we denote the corresponding indecomposable object V lambda mu. And well, it's clear that if lambda is a partition of R and mu is a partition of S, then V lambda mu is a direct summand in the object RS. And moreover, like this description of V lambda mu, that it's mapped to Z lambda tender Z mu, it says us that actually V lambda mu is the sub-object, is a direct summand in the object that is, we can take the Schur factor S lambda and apply it to V, and we can the product is Schur factor S mu and apply it to V also. So V lambda mu is sort of like the highest weight in terms of sub-object in this tensor product of two Schur factors to Schur, I mean, applied to V and V dual. Okay, so also, so last thing I want to say about the link categories is that they actually satisfy a very nice universal property. So if D is a symmetric tensor category, then the set of isomorphism classes of all tensor functors from Webglt to D is in bijection with the set of all isomorphism classes of objects of dimension T in D. So we just map our functor F to its image on our T of our object V of dimension T. So it's clearly maps to something of dimension T. And so yeah, so this is a bijection.
There's no condition on F. It's just a
I mean, it's a tensor fund. So,
no.
and as a corollary of this, we get that there is a symmetric tensor functor F when T is equal to some positive integer. We get the symmetric tensor functor from Webglt to the category of representations of the group GLM over C. And we map our generating object V to Vn, which is a total logical n-dimensional representation of GLM. And I mean, it's a natural question to ask. So yeah, but we have integer T. How do these categories compare to each other? So Webglt in the category of representations of GLM. And so we have this functor, but what can we say about it? Well, first of all, it's clear that it's not faithful. This is because, so we have that endomorphisms of our object V of the K tensor power. So if we have the category with tensor power P, then endomorphisms of this are given by the group algebra of the symmetry, right? And if we now plug in n-dimensional vector space into here, and K is greater than n, then the skew symmetrizer will act by 0. So not faithful. But it turns out that this functor is essentially surjective and full. So yeah, but so Webglt will be larger than Webglm. So let's see how this functor acts on our indecomposable object. So if you have two partitions, lambda and mu, such that length of lambda is L, length of mu is M, and N is greater or equal than L plus M, we can define the following weight of GLN. So I denoted lambda mu n. So we first take the parts of the partition lambda in the decreasing order, then a bunch of zeros, and then the reversed parts of like the parts of mu in the increasing order with minuses. And yeah, so and we want the length of this vector be n, so that it is a weight of GLN. And it's clearly an integral dominant weight because lambda and mu were partitions. And now if if t is equal to n and it's greater than L plus m, then our object V lambda mu is mapped to the irreducible representation of GLN with this highest weight, lambda mu n. And if n is less than the sum of two lengths, then this object is just mapped to 0. And lastly, I want to say that it turns out that our category is Webglt. So a priori, we define them as some Cherubic envelope of something. So they are at best Cherubian. But it turns out that when t is not an integer, then they are abelian and semi-simple. So yeah, so this is just some preliminaries on the link categories. If you have any questions on this. Yeah, so I just want to stress like this correspondence between representations of GLN and objects of Webglt given by this functor. So to bipartition lambda mu, we assign this highest weight. We'll see the highest weight in the later. Okay, so now I want to talk about the ultra product construction. So yeah, I'll start by defining what an ultra filter is. So an ultra filter F on a non-empty set S is a set of subsets of S that satisfies the following properties. So if we have two sets, U1 and U2 in F, then their intersection must be in F. If for any U in S, exactly one of U and the complement of U is in F. And lastly, if U1 is a subset of U2 and U1 is an F, then U2 must also be an F. So there's a nice way of thinking about ultra filters as F2 valued characters of the ring of F2 valued functions on S. So how do we do this? So F2 valued functions on S clearly are in bijection with subsets of S. And now if we look at some character and we look at which subsets, on which subsets it takes value 1 rather than 0, and then this set of subsets of S will actually, you can check that it defines an ultra filter. So the property of being the character and respecting the multiplication and summation in this ring, then it will translate to these three properties of the ultra filter. Okay, and an easy example of an ultra filter is that we fix some element S in S, and we take all subsets of S that contain this fixed element. And this ultra filter that we get is called the principal ultra filter. And it's easy to check that if S is a finite set, then all, so on the level of characters, this corresponds to the evaluation characters. You just evaluate the function on this fixed element S. And if S is a finite set, then all characters are evaluation characters and you get nothing else. But it turns out that if S is not finite, then you get something that is a non-principal. So for us, it will be important for the set, for countable set S, so namely we take set of natural numbers. And it can be shown that there exists a non-principal ultra filter on N, and it also, well, it can be shown that such ultra filter must contain all cofinite sets. But I warn you that the proof of this is not constructive. We don't know how it looks. It just uses Chorn's lemma. So some ultra filter exists. And so let us fix a non-principal ultra filter F on N. And then we can, if you have a collection of non-empty sets Xn labeled by natural numbers, we can define the ultra product as the quotient of the product by the equivalence relation, where we say that two sequences of elements are equal if they are equal for almost all k. This means that they equal for all k in some u in our ultra filter. And this definition can be modified slightly so that we can include some empty sets, but let's not do this now. So yeah, so this is a definition of ultra product. And there is a nice theorem by Wasp that roughly states that any first order language statement that is true for almost all Xn's is also true for the ultra product. And how we're going to use this is, so we will need this just for a few examples. So if all Xn's had some algebraic structure, for example, they were groups, algebras, and fields, then the product is also a group, algebra, and field. And the ultra product inherits this algebraic structure from the product of this Xn, and it will also have this structure. And now if Xn are vector spaces over some fields Fn over the corresponding fields, then the ultra product will be a vector space over the ultra product of the field.
Is it important if F is not the principal one, or it can be in the old?
I think for the principal one, you'll get something very important. yeah, something just boring. So you'll just get one of them. I mean, I'm not sure, but
Okay,
just to get something not boring. And yeah, okay. And now let me warn you that there's a non-example. So just a statement for which you cannot use the Voss's theorem. So if VNs are finite dimensional vector spaces, then the outer product is not necessarily finite dimensional. So you cannot express finiteness. And however, so if we require that the dimensions of VNs are bounded for all n by some universal constant for all n, then the outer product will be finite dimensional because the property of being a basis is preserved. Well, it's a first order logic statement. And now, so last example that we're going to use is the following. So let us take Fns to be the fields of algebraic numbers. This is just the algebraic closure of Q. Then the outer product by Voss's theorem is going to be an algebraically closed field of characteristic 0. And it can be checked that the cardinality of this field is going to be continuum. Therefore, we can use Steinitz theorem and say that there is some non-canonical isomorphism of this field with this field of complex numbers. Now, finally, so if we have a collection of small categories Cn labeled by natural numbers, then we can define the outer product of this category. So we take, well, the objects of C are just the outer product of objects of Cn. And if you have two objects, X is the outer product of Xn and Y is the outer product of Yn, we define homes between them as the outer product of the corresponding homes. So in particular, we see that if we enrich like our category, so if it was C linear, then the outer product will also be like C linear category. And now the theorem due to the link says that so if T is a transcendental complex number, then the category Webglt can be realized as some subcategory inside the outer product of categories of representations of GLN. So in the following way, so we take the Karoubi envelope of the symmetric rigid monoidal subcategory in the outer product of categories of representations of GLN over Q bar. And we take the subcategory that is generated by a single object V, and now V is defined as the outer product of Vns, where Vn is a tautological n-dimensional representation of GLN over Q bar. Now we need to pick a right C-linear structure for this category, and we do this in the way that V has dimension T. So we choose an isomorphism between the outer product of Q bars with C, such that it sends this 1, 2, 3, and so on to T. This is because Vn has dimension m. Okay, so this is the theorem by Delisle. And so it's clear that we can only obtain transcendental T's in this way, because there is no polynomial that has zeros in every positive integer. And if we want to include algebraic values of T, so we will need to modify this theorem slightly. So this result is due to Nate Harman. So, and it states that we can do the same construction for algebraic T, but instead of Q bars, we will need to take some fields of positive characteristics. So we'll take FPN bar. And then, so if these PNs are different for all n's, if they tend to infinity, then the characteristic of the outer product of this field will still be 0, and it will still be a field of cardinality continuum. So it will still be a C-linear category that we get in the end. Yeah, but let me, for simplicity, assume that T is transcendental from now on, and will only work in characteristic 0. Okay, so this is Delisle's theorem, the outer product construction. So one note I want to say that, so note that V is the outer product of this Vn's, and guess what our objects V lambda mu are the outer product of. Yeah, So recall that we had this lambda mu and the highest weight, so that they will be the outer product of these three lambda mu n's. Okay, so that's it, and I just now want to go to the second half and discuss the Harish-Chandra modules. Maybe any questions about this? None in the Zoom as well. Okay, then I'll go to the second half. Okay, so let's do some representation theory in Webglt. So we can define the real algebra object, GLT, that is as an object is just V tensor V dual. And as an outer product, it's going to be just the outer product of three algebras GLN. And note that these GLNs, they act on objects in the corresponding categories. And therefore, like, it's easy to see that GLT acts as well on all int objects of Webglt, and we will refer to this action as natural. We can also define the universal enveloping algebra in the way we would do this for usual algebra, right? We just take the tensor algebra and we quotient it out by some standard commutator relations. And the tensor algebra has the filtration. I mean, it's a graded algebra, and the universal enveloping algebra, therefore, will inherit the Poincare-Bergov-Witt filtration from this tensor algebra. And now we can realize FKU, the case filters component of U, as the outer product of FKU of GLN, where here FK denotes the standard PBW filtration on the universal enveloping algebra. Note that I need the filtration here because this outer product construction was only defined for Webglt, not for the int completion, and U is naturally an int object rather than an object in our case. So when we deal with int objects, we always need to keep track of filtrations. Now, if Z is the center of U, we can realize it as homes from the unit object to U. So if something commutes with the Lie algebra GLT, it also commutes with the action of the group GLT. So it's it's going to be like the unit object. All copies of the unit objects inside U considered as an adjoint via adjoint action of GLT on it. And now, so it also inherits these filtrations, and we see that FKZ is the outer product of FKZ of U of GLN, and we know what the center of U of GLN is. So it's the polynomial algebra with generators in each degree, C1 through n of degrees 1 through n, and the filtration is the filtration by degree. So we can easily compute the outer product, and we get that this is a polynomial algebra in infinitely many generators, Z1 and so on, Z1 to 2, so on, and the degree of zk is equal to k. Now, moreover, we have outer product construction. Let's use it. So we can, all of this can be done without any outer product construction, but now with outer product construction, we can actually specify a very particular choice of generators in C. We take Zi to be the outer product of Zin, and Zin is some central element in U of GLN, and we have the Harish-Chandra isomorphism for U of GLN. So we need to fix some polynomial that is on the set of weights of GLN that is invariant under the action of the while group, and the while group for GLN is symmetric group. So we just want to fix some generators in symmetric polynomials in n variables. And my choice will be the power sum polynomials. So Zin is going to be in a central element that acts on the Verma module m chi with the highest weight chi minus rho via the i's power sum polynomials on the coordinates of chi. Okay, and now given a central character theta from Z to C, we define the exponential generating function of theta as usual. So we just take 1 over I factorial, theta of the I, U to the I. And this is just, so because theta is determined by its values on the generators, it's just a compact way of storing information about the central character. Okay, so this is some preliminary definitions. Now I want to define Harish-Chandra bimodules. And I want to do this in the way, in the most general way. So I will define Harish-Chandra bimodules in some general symmetric monoidal category. For us, it will be either the category Webglt or the category of representations of some reductive group G over C. So it was classical case, yeah.
Sorry, your central elements, do they depend on the choice of triple two?
They do, yes. Okay. But it's just, yeah, I mean, we'll, with a fixed choice, yeah, we'll just store some information about them.
And here you assume T is transcendental?
Yes. Yes, I want to assume T is transcendental. I mean, here, right now, I'm just, I assumed it mostly here because I had some calculations with, yeah, but we still, I mean, for non-transcendental T, we'll work with positive characteristics, and we'll still have Harish-Chandra center of the universal enveloping algebra, and it will still correspond to this. But let's just not, let's just assume that we only work in characteristic zero, then T will be transcendental. Yeah. Here, for us, it will be our category in which we work will be either Webglt or just the category of representations of some reductive group G. And then we can define the Lie algebra object G in C as well, for Webglt, it will be just our algebra GLT that we defined before. For the category of representations of some group, it will be just the corresponding Lie algebra. And it acts naturally on all int objects in C, and yeah, and I refer to this action as natural. And I want to remark that we can actually do this for any symmetric tensor category. We won't need this for results, but in any symmetric tensor category, you can define a so-called phi1 of C, the fundamental group of C. It's some algebraic group, affine algebraic group scheme in C, and to it you can assign the corresponding Lie algebra object, and it will act on all objects of C. So actually, like, this is well defined for a wider range of categories. But for us, like, only these two examples will be important. And so let me fix some notations. So G opposite will be the Lie algebra object with the opposite bracket. U square will denote U of G tensor U of G opposite. Z square will be the center of U square, and there is an isomorphism with Z square and the tensor product of two copies of Z. Now let K be the anti-diagonal subalgebra inside G plus G opposite, and it is isomorphic to G. Then, so how is this subalgebra characterized? So we can consider any U square module Y in int C as a U bimodule, right? Because the left action of U of G opposite is the same as right action of U of G. And then K is such a subalgebra. If you restrict Y to K, you'll get, well, this action, this G module is the same as considering the adjoint representation on Y as a bimodule. So this is what K is. So you just, when you restrict to K, you just consider the adjoint action on the bimodule. Okay, so this is some notations. Now, I say that a U bimodule in C is K algebraic. If the action of K, this is isomorphic to G, coincides with the natural action, then, yeah. So let me note that K algebraic bimodules are the same as left U modules in C, because in C, you already know what the diagonal action is, right? So it's a natural action. So all objects of in C already come with some action of G. So you only need to define the second action, the left action. Then you can recover the right action. Just a quick note here. And now we say that the U bimodule is finitely generated if it is a quotient of U tensor X tensor U for some X in C. So in this bimodule on which the left copy of U acts by left multiplication on here, and the right copy acts on the by right multiplication on the right copy of U. So it's some sort of freely generated bimodule, and it is generated by objects X in C rather than in C, and therefore we call it finitely generated. So all objects of C will be like analogs of finite dimensional objects for us, as opposed to int objects. And we say that Y is generated by X in this case. And so let me state a nice example of a bimodule. We'll use it a lot. So we can take the tensor, so if X is in C, we can take the tensor product of X with U as left U modules. So therefore, like the right action of U on this tensor product will be just by right multiplication on U, and it won't affect X. And the left action is just the action on the tensor product. So on X it acts diagonally, on U it acts, naturally, on X it acts naturally, on U it acts by left multiplication. And so it's easy to see that phi X adjoint is just the tensor product of X and U adjoint. And the adjoint action is the natural action. And so, well, U adjoint is just the symmetric, isomorphic to the symmetric algebra of G. So our phi X is K algebraic. Yeah, so I wanted also to note, so if you've seen the definition of Harish-Chandra modules or bimodules before, so you probably know that K algebraic means that the adjoint action on Y, or Y's restriction to K, is a direct sum of finite dimensional things, so finite dimensional K modules. So this natural condition is sort of the same, because we consider objects of C as finite dimensional representations of K. So here you see that phi X adjoint is X tensor the symmetric algebra, and symmetric algebra is the direct sum of finite dimensional representations, right? And so this bimodule is finitely generated because it is a quotient of U tensor X tensor U, like with the same X. Okay, now I want to finally define Harish-Chandra bimodules in C. And I want to do this in the way that is compatible with the classical definitions. I want to, when I say that C is a category of representations of group G, so I want to receive the output I want to get is just the classical Harish-Chandra bimodule. And it turns out that there are two ways to do this. So let Y in C be finitely generated K algebraic bimodule. So we can do the classical definition, stating some sort of admissibility condition. So we can say that the multiplicity of every finite dimensional, of every X in C inside Y adjoint is finite. So this will work for us, but there's also a second condition that we can try, is that we ask that the Z square acts finitely on Y. This means that the annihilator inside Z square of Y is an ideal of finite codimension. And it turns out that condition 1 always implies condition 2, so it's always stronger. I can sketch the proof for this. So Z square commutes with the action of K, so it acts on multiplicity space of X inside Y adjoint. And since this is finite dimensional by assumption, then the annihilator of this multiplicity space is going to be an ideal of finite codimension. And now if we take X such that it generates Y, then we'll see that actually annihilators should coincide. So the condition 1 is always stronger. Let me write this again. And now, why do we want the two conditions? Why do we even consider both these conditions? This is because in the classical case, we cannot actually distinguish between them. They are so the condition 2 implies condition 1 as well, so they are equivalent. And this is a corollary of Costam's theorem, and which says that which describes the universal enveloping algebra as a module over its center. So from this theorem, you can also recover the equivalence of the two conditions. And why do we need two conditions? So let's have two definitions for the two conditions. So I will use the more general ones. You say that to define Harish-Chandra bimodules. So we say that Y is a Harish-Chandra bimodule if it satisfies condition 2, that is the center X finitely on Y, and Y is the K algebraic finitely generated bimodule. And I will denote by HC the corresponding category. And I'll say that Y is a Harish-Chandra bimodule of finite K type if it satisfies condition 1, that is the multiplicities are finite. And we need the two separate definitions because in the complex rank case, they are not the same. So an example of this is the following. So we take theta to be some central character, and we can define U theta to be the quotient of U by the ideal generated by the kernel of theta. Then U theta is naturally a Harish-Chandra bimodule because, we can act on the left by left multiplication, on the right by right multiplication, and we'll see that both copies of the center act via some central character, so the center acts finitely. And it turns out that it's not of finite K type. And rough intuitively speaking, this is also a corollary of this constants theorem. And so what does the constants theorem say? Can I? No, I probably cannot do this. Okay, so let me read this. So the constants theorem says that the multiplicity of some finite dimensional module V inside U theta, adjoint, is equal to the dimension, the dimension of this whole is equal to the dimension of the zeroth weight space of V. And when we look, if we want to interpolate this, so we can see that, roughly speaking, these dimensions of the zero weight space, they depend polynomially on n. And in the limit case, you will get something not finite dimensional. I mean, it's not a rigorous proof, but this is the intuition behind this. So you cannot obtain something finite dimensional. And so this is unfortunate. So we definitely want to work with this U theta. So they are quite nice bimodules. So we want to include them into the definition of Harish-Chandra bimodules. But a lot of interesting things will happen because of the difference of the two definitions. Okay, so now, because we have this finite action of the center, we get a block decomposition of the category HC. So HC is the direct sum of categories HC tilde theta 1, theta 2. And by this, I mean the subcategory on which the center, which is isomorphic to Z tensor Z, acts with generalized central character theta 1 tensor theta. Now the question we want to answer is for which pairs theta 1 and theta 2 is this category non-zero? And I want to remark that we can actually consider some simpler subcategories, HC theta 1, theta 2 without the tilde. This is going to be a subcategory in which Z square acts via non-generalized central character theta 1 tensor theta 2. So, and it is clearly enough to answer this question for these categories because any object in this HC tilde has a filtration has a filtration. So, if you have a non-zero object in HC tilde, then it will have a non-zero quotient in HC without the tilde. So, clearly enough to answer for these categories. And before I do this, so let me state a quick lemma. So any object Y in HC theta 1, theta 2 is a quotient of the bimodule phi x of theta 2. And it is a notation for the bimodule x that is an object, is just the tensor product of x with U theta 2. And it is the same bimodule that we had before, but we quotient out by the action of the center on the right. So on the right, the center will act via the central character θ2. Okay, and I mean, it's an easy lemma, but I don't have time to prove this. And now let me state the answer in the classical case. So yeah, so for the classical case, the classification of central characters is very well known, and it's the following. So let C be the category of representations of some reductive group G. Then HC of θ1, θ2 is non-zero if and only if there exists Verma module MK1 and MK2, such that the center acts via this central character θi on MKi, and such that the difference of two highest weights lie in the lattice of integral weights of group G. That means it is a weight of some finite dimensional representation of G. So yeah, so roughly speaking, yeah, we have two central characters. We look at some corresponding highest weights, and we want the difference of these highest weights to be in the integral lattice. And the idea of the proof is the following. So any module by the lemma that we had on the previous page is the quotient of phi x of θ2. And so it's enough to work with these bimodules. And the center acts via if the center acts via θ2 on some MK, on the Verma module MK, then we have so use of θ2 embeds into linear homes between into endomorphism algebra of MK just by the action, because U of θ2 acts on MK, and it is well known that this map is an embedding. And therefore, for f phi x of θ2, we'll get an embedding of x tensor u θ2 into just homes from MK to x tensor MK. And now if you want to understand the left action of the center on this bimodule, it's enough to look at this action of the center on x tensor MK. And x tensor MK has filtration by standards, by other Verma modules, MK plus lambda, and lambda runs over the multiset of weights of x. So it's clearly in the integral lattice for group G. So yeah, so this implies this statement. And now I want to give the statement for the context rank case. It will look different, but I want to break down this afterwards and say why this is the generalization of the classical case. So let's see the Webglt. Then the theorem is the following. So the category HC θ1 θ2 is non-zero if and only if the difference of these exponential generating functions of θ1 and θ2 is given by this formula. And I mean, this formula clearly depends on our choice of generators, on the choice of ultrafilter, just the way of storing information. And so you see we have some differences of exponents, and this is like, it's not zero if and only if this formula holds for any R, for any S, and for any complex constants BI and CJ. And let me give you the taste of what the answer looks like in the non-type A case. So if we work with categories rep OT and rep SP2T, then this category is non-zero if and only if for some R and for some constants BI, this difference of exponential generating functions is given by difference of hyperbolic cosines. And I want to break down the differences that we get in the two cases. So the first thing that we see is that instead of exponents, we get hyperbolic cosines. And this is due to the fact, this is due to the way we chose generators. So recall that we chose generators as some W invariant polynomials in a set of weights. And for the case of GLM, it will the W was just a symmetric group, so we picked just some symmetric polynomials, the power sum polynomials. And in this case, W will be, roughly speaking, for enough for almost all cases, it will be the semi-direct product with the symmetric of the symmetric group Sn with z mod to z to the n. And so the invariant polynomials that we'll get, so the group acts by changing the sign of our variable and as well as permuting. So we can take the generators that are even power sums, right? Just the symmetric polynomials in the squares of our variables, and even power sums will get us, so we will get only summation over even parts. Instead of exponents, we'll get hyperbolic cosines. And so this part is similar. So we also get bi plus 1 minus bi, the same as here, but we don't get this negative part here. And this is due to the fact that in these categories, the object B, the generating object, is self-dual. And so this is sort of, the minus part sort of corresponds to the V-dual part. And now I want to sketch the proof for this. Do I have time for this? Like, I'll probably sketch the proof and it's good. Okay, I see. So that's, I see, okay. Yeah, so I want to sketch the proof for this. And you'll see how it compares to the classical result. So we start by noting that, well, any bimodule, again, is a quotient of this phi x of theta 2. And any x, well, reasonable x and incomposable x is a quotient of the generating object Rs. And now we want to understand for which central characters theta 1, the quotient is that I denote phi x of theta 1 of theta 2. This is the same bimodule we had before, but now we also quotient out by the kernel of theta 1 on the left. So we take the double quotient by theta 2 on the right and by theta 1 on the left. And we want to understand when it is non-zero. And as I said, it's enough to take x to be this generating object Rs. And now we want to do induction on the sum R plus S. And we will do this sort of in a classical setting, and then we'll take the ultra product. And now I want to give you an example of this computation in the easiest case. So for this, let me fix a notation. So let eta be the map that sends a weight to the corresponding central character, just to fix the notation. And then, so I want to do the computation when Rs is equal to 1, 0. Just the base case for our induction. And so Rs is 1, 0, so we work with phi v, and we do this in classical settings. So we work with phi v n of theta 2. And we want to understand which left central characters appear in this module. And we do this very similarly to what you had before. We embed this tensor product into homes between m chi and vn tensor m chi. And here, the corresponding central character for chi is theta 2, so that we had an embedding of theta 2 into endomorphisms of m chi. Now, again, so we want to understand for which theta 1 appear here. And this is, for this, it is enough to see which central characters appear in this tensor product. And we've seen before that they are precisely eta of chi plus ei, where ei runs over, like e1 through en are weights of this n-dimensional tautological representation of GLM. Right? And now we do the computation. So our eta of chi plus ei will be our central character theta 1. So let's compute the exponential generating function. So we compute these central characters on these generators, zkn, which were defined as the case power sum polynomials. And so when we add ei, we just shift the i's coordinate of our weight chi by 1. So, and this computation that we get is precisely the case power sum polynomial of chi when we shift the i's coordinate by 1, right? And now we take the difference of theta 1 and theta 2 of u, right? So this is chi, the central character that corresponds to chi plus ei, and the central character that corresponds to chi. And it's the same as like taking the exponential generating function for this difference. And yeah, you see that this is going to be just the difference of two exponents, and the coefficients, they differ by 1. this is very similar to what we had before. When we take the ultra product, we get that θ1 of u minus θ2 of u is the difference of two exponents for some complex number b, right? So let's compare to what we had before. You see here, very similar, but what happens? So we don't get this negative part, and here we only have one summand. And this is due to the fact that we took r equal to 1 and s equal to 0, right? Just very compatible with what we had before. Now the question is, which complex number can appear here? So, you know, then in the classical case, these coefficients were chi I, like b was equal to chi I to some coordinate of the corresponding weight. So it's a very finite number of numbers that you can get. And well, it turns out that in this complex range situation, we can get any value of b, right? It can be any complex number. You can always do this magic tricks with ultra products when you only change the finite number of numbers, and you still obtain the any amount you want. Any b works. And I guess so. This start the difference between what we have in the classical case and what we have in the complex range case, like very finite number of possibilities here, and even non-countable number of possibilities here. And this is due to the fact that we had two definitions of Harish-Chandra bimodules. So actually, like the well-behaved Harish-Chandra bimodules are the finite K-type bimodules. So they will have finite lengths, and this general bimodules won't have finite lengths anymore. So it's, they are not very well behaved, and yeah, that's part of the reason why it's more difficult to have the classification of, for example, simple objects in this category. So it's that they will be much more of them. And yes, I don't really know now the classification of simple objects here. And if I still have a few minutes, let me just say a few words about finite K-type bimodules. So, yeah, as I said, so if y1 and y2 lie in HT θ1 θ2 and y2 has finite K-type, then the dimension of Holmes between y1 and y2 is finite. And as a corollary of this, we'll get that if we have, so any bimodule of finite K-type has finite lengths. So they are nicer in some sense. And so let me sketch the proof. So y1 is a quotient of phi x of θ1, θ2 for some x. And so the dimensions are bounded by this Holmes from phi x, θ1, θ2 to y2. And y2 is already assumed to lie in this category, so we can forget about θ1 and θ2 on the left. And this is the same as Holmes from phi x to y2. And this is also a nice exercise that I didn't have time to cover. So lemma, actually Holmes from phi x to any bimodules are the same as Holmes from x to the adjoint of this bimodule. So very nice bimodules phi x. Very easy to prove, but don't have time to do this. And this is finite by assumption. So yeah, so we get the finite Holmes. And the problem with the finite K-type bimodules are that we don't really know how to describe them. What are they? Like, how do you even construct the examples for them? Are there any finite K-type bimodules? Can you think of some? Well, the easy example is that we take finite dimensional things and we just take the tensor product and consider it as a bimodule. Then it is actually clearly a finite K-type bimodule because we already took something finite dimensional. And there are other examples that I constructed. And so let me quickly state. So the idea is that we want to take filtered ultra product of classical Harish-Chandra bimodules, filtered because we are not allowed to take ultra product of infinite dimensional things. So we need a filtration. And the idea is you take some bimodules yn for GLN, you take some filtration by finite dimensional K modules that agrees with the PBW filtration on U square. And you define, you take the ultra product of this fk of yn. This way you define fk of y. Then you take the union of this filtered component, and you obtain something that has an action of u square on it. But what you get is not necessarily even an object in Webglt. So a priori it lies in the outer product, right? And Webglt, it was only a small subcategory in the outer product. So in order to land in our small subcategory, we need some requirement on the multiplicities. And the requirement is the following. So we need that for any bipartition, nu prime, the multiplicity of this V with the corresponding highest weight is finite in every filtered component, or is constant for, and therefore in the outer product it will be the same. So it will be well defined. It will be finite. But this is a very weird condition. But now, if you want to obtain a bimodule of finite k-type as a result of this, we actually need to require that these multiplicities in yn of each finite dimensional thing with fixed nu and nu prime for all n is constant for almost all n. Not in the filtered component, but in the whole infinite dimensional bimodule. And in this way, the result won't depend on the filtration, and you will get a bimodule of finite k-type. And so this problem of classifying finite k-type bimodules, it's essentially finding sequences of bimodules for GLN for which this condition holds. So you need to understand pretty well the multiplicities in Harish-Chandra bimodules and take this ultra product of things for which this is constant. And what I was able to do is that I don't really know how to compute this in general, but there's something that can be said about finite dimensional bimodules. So if you take bimodules that are just linear homes between two finite dimensional things, and you take some sequences of highest weights, lambda n and mu n, so there are some assumptions on sequences that you can put on them, and roughly this assumption is that you consider them as partitions, and you look at the corresponding Young diagrams, and you require that the length of the diagonal of these diagrams are constant for Ln, and or bounded, which is the same for the ultra product. And in this case, you can actually prove that these multiplicities won't depend on n, so they will be constant for almost all n. And yeah, so and this allows you to define some bimodules, finite k-type bimodules in Webglt, and in some sense they interpolate finite dimensional bimodules, but they are not finite dimensional anymore. And they will be simple, and so they're also like this subcategory generated by these bimodules is stable under multiplication, tensor multiplication with V and bimodules. You don't construct new bimodules when you tensor them with finite dimensional things. You can also study some categorical actions of SLD, like type A action, when you have this tensor product with V and bimodules. But yeah, so this is the best I was able to do now. I don't know if it's in any sense a full classification. I expect that, I mean, my hope is that you don't have any stuff giving really different examples of bimodules of finite k-type. So they are either interpolate finite dimensional stuff, or they are in some sense submodules, like sometimes so this things you get in general, you assume so the combinatorial data you assume is in some sort of general, so that you get in the end something that is transcendental and not degenerate, and you can still get some degenerate cases, but the hope is you won't have anything very different from what is constructed. Yeah, I guess that's it. So I had like this some picture on the assumptions. So you sort of you assume for your highest weight that the diagonals are fixed. But yeah, this is pretty much the assumption. Yeah, that's it. Thank you.